Okay, so here's the review for this next test. So it's chapters 17, 18, 19 as far as homework is concerned. Um, so we start off chapter 17 talking about current. And current is the rate of change of the charge with respect to time. And so the units of charge are coulombs and the units for time are seconds. So we have coulombs per second, which we call amperes. I have a special name for that. Now, most of the time you'll just be given the current instead of giving the rate of dealing with the rate of change of current. A lot of times that happens with when we develop the differential equations for the capacitors and the resistor type circuits, which we've already covered in the previous test. So we're not covering RC circuits for this semester, this particular test. The main next thing is Ohm's law, and what Ohm's law does is it relates the current, the voltage, and the resistance through a ohmic element. So you typically, you're talking about some kind of resistor, which we show as such, and across the resistor is some voltage difference. So we can call that delta V voltage. And then there's the current that's flowing through the resistor, and then the resistor has some value R in ohms. So Ohm's law says one thing is for these elements, these resistive elements, which we call resistors, there is a linear proportional relationship between voltage and current. So it's the voltage divided by the current. So there's different versions of this equation just depending upon what you solve for. So, if you apply a voltage across a resistor, then the current through the resistor is the voltage divided by the resistance. If you have a certain current going through the element, then the voltage is going to be the current times the resistance. But they're all the same equation, just solved for different things. And we give the resistance, the units for resistance are the units for voltage, and I guess I should put delta V here instead, delta V. So the units for delta V are volts, and the units for current are amps, and so we call volts per amp ohms. And remember, if you have 1 kilo ohm, that's 1,000 ohms. If you have 1 mega ohm, you've got 1 million ohms. So a lot of times we have resistors that are, larger than a couple of ohms. They're on the order of thousands or millions of ohms. And the resistance of a particular material is related to the material properties of that. So the resistance is equal to the resistivity times the length divided by the area. So our rho is the resistivity, and it depends upon what the thing's made out of. And that has units of ohm meters. And A is the cross-sectional area. So depending upon what the shape of the cross-section is, you're going to use the appropriate area formula. So it might be square, it might be circular. So make sure you write down if you don't know, the area of a circle and the area of a square and the area of a rectangle. We're probably not going to use triangular wires, and L is the length. So the smaller the area, the bigger the resistance. The larger the resistivity, the bigger the resistance. the longer the length, the bigger the resistance. And the units here, make sure there's in meters squared for area. Length is in meters. So, a kind of problem that I might give you here is, I give you some kind of element made out of some material. And so I'm not showing it as a resistive element, I'm just showing it as an element of some length. I guess you could think of it as maybe a better way to look at it would be just kind of like a black box here. So I'm not showing it as a resistor, but it's some material. So what we're assuming is that we're going to apply some voltage to this, say 5 volts, and that these leads have 0 resistance, and then we have the resistive element, and this resistive element has some length L, and it has some cross-sectional area. So here, this is A, cross-sectional area, and it has some material properties, the resistivity. So, what I could give you is, say, if material is gold, and then I would give you what the resistivity for gold is, which I don't know exactly what it is, so I'm going to make it up, 2.5 times 10 to the minus 8 ohm meters, and I give you a length. Let's say the length's okay, so let's say the length is 100,000 meters, and the radius is 2 millimeters. So if I give you all those things, you can't. You have to calculate. You have to calculate the area, and let's say it's 2 millimeters in a circular. So you calculate the area, which would be pi r squared. If it's diameter, you'd have to divide the diameter by 2, and you would need to convert millimeters to meters, so you'd multiply it by 10 to the minus 3, so it would be 2 times 10 to the minus 3 meters, and you'd square that, so that you'd end up with meters squared. So then, so we take pi times 2. Let's see what I got here. Let's try this again. Pi times left parenthesis 2.0 e to the minus 3 power squared. And usually that number comes out pretty small. Cross-sectional areas of these kinds of things are pretty small. And we would get 1.26 times 10 to the minus 5 meters squared. So then you could calculate the resistance. The resistance would be equal to 2.5 times 10 to the minus 8 ohm meters times the length, which is 100,000 meters, divided by 1.26 times 10 to the minus 5 meters squared. So let's plug that in there. 2.5 e to the minus 8 times 100,000 divided by 1.26 e to the minus 5, and I get 198 ohms. So you can see for conductors the resistances are pretty small, even 100,000 meters, which is 100 kilometers. Okay, and this is a fairly small wire. Obviously, you're not going to make resistors out of resistive elements out of conductors, but this still would be applicable because you're going to have cases where you're trying to transmit power and you want the resistance to be as small as possible. So from that, if I told you then, given that resistance, if the voltage from one end of that to the other is, say, 3 volts, you could use Ohm's law to figure out the current through the wire. And so you'd have 3 volts divided by 198 ohms, and you get the units that are appropriate for current, which are amps. So you get 0.0152 amps using a capital A. Or you could say it's 15.2 milliamps. So if you multiply this by 1,000, then you get milliamps. Okay. Now I'll come back to that in a little while. I could use that, I could calculate the magnetic field around that wire at a certain distance using some of the stuff that I learned in chapter 19. So I might combine this with some other stuff. Okay. Now it turns out that there is the resistance is a function of temperature. So I could say R is a function of temperature, and the resistance, the temperature, the equation is you have this kind of resistance at some standard temperature, which is usually 20 degrees C, and then you add, so you take 1 plus alpha, which is called the temperature coefficient of resistivity, which is again a material property, and you multiply that by the difference in temperature between the temperature you're interested in and the reference temperature. So T0 is usually 20 degrees C because that's normal room temperature. And so I might ask you to figure out what is the resistance at T equals 75 degrees C, and all you'd have to do is take your reference resistance, which I would have to give you, and then you multiply it by 1 plus alpha. And so let's just give you some numbers here. Let's say R0 is 100 ohms and the temperature coefficient is 0.002, and the units would be so they have to have units that are going to work out. So because T is in degrees C, alpha has to be in 1 over degrees C. So when you multiply degrees C by 1 over degrees C, you end up without any units. So in our case, so now that we've got some numbers here, you would take your resistance at 20 degrees C, you take 1 plus alpha times the difference in temperature, which would be 75 minus 20. And it does change some. It doesn't change a huge amount, but it does. I mean, it's significant if the temperature difference is big enough. So you take 1 plus 0.002 times the quantity 75 minus 20, which is 55. And so you get, in terms of the print, determine the brackets here, which I'm going to now make in parentheses, 1.11. So that's 11%. So the resistance increases by 11%. So you take 1.11 multiplied by 100, and you get 111 ohms. So that's the temperature. The resistance at 75 degrees C. The resistance at 20 degrees C would be just equal to 100 ohms. And then finally, say for example this previous problem, if I said, how much power is dissipated in this circuit? Well, there's a couple of expressions. One, which applies all the time for any kind of element, is the power is the current times the voltage. For resistive circuits, which is what we have here, it's I squared times R, and all I'm doing to get from here to here is using the resistance is voltage per current, voltage divided by current. So if you plug that in if you solve for V and plug that in, you'll get that. Or if you solve for I and plug it in, you'll get V squared over R. These are for resistors or resistive elements, which could be just wires. This is always true. So, if I wanted to ask the question, how much power is dissipated associating with this problem, all I have to do is say power is equal to I squared R. The current is 0.0152 amps. Square that times the resistance, which is 198 ohms. Plug that in, you get 0.0152 squared times 198. So that's 0.0457, and the units for power are watts. So put that up here, watts. Remember, watts are equal to joules per second. It's energy per unit time. Now if I use the other expression, V squared over R, the voltage was 3 volts. So I'd have 3 squared over R, which is 198 ohms. So 3 squared divided by 198, I get the same number. And also, if I took, so that's power, not resistance, but power is also voltage times current. So if I did that, I've got current, which is 0.0152 amps. That's current, so let me put that in the right place. The voltage is 3 volts. The current is 0.0152 amps. And I multiply that together, 3 times 0.0152, and I get 0.0456, which that's just because I rounded this off to 3 decimal points. Okay, so you can see it doesn't matter which one. And it's because I used Ohm's law over here to relate current to voltage, so that's why they all come out equivalent. So that is chapter 17. Basically just talking about Ohm's law, the units for Ohm's law, the definition of current, how temperature affects resistance, and how power is calculated. Okay, for the next chapter, you've got resistors. Okay, so now we're going to talk about resistors in parallel and series. Now, we talked in the previous test, we had capacitors in parallel and series, and the difference is that the equations are different. Okay, so in series, for resistors, the equivalent resistance is just the sum of the resistors, whereas for capacitors it was 1 over the equivalence resistant capacitors. So I just realized I spelled parallel wrong. That didn't look right earlier. Parallel. Okay, parallel. So for parallel, you get 1 over the equivalent resistance is equal to 1 over the sum of the reciprocals of the resistor. So again, you have to make sure you once you add these together, you have to take the reciprocal at the end. Don't just add them together like this and that's your answer. It's the reciprocal. Now, since we did one of these in class, I'm not going to do it again. But basically, you're going to start with a circuit that consists of a bunch of resistors in parallel and series. So, in this case, I might have another one here, and then I could have these two be parallel like this in that grouping, and then come all the way around with some kind of voltage and go up here. So this would be R1, this would be R2, R3, R4, R5, R6, R7. So the way you would simplify this is you would take the most inner grouping of the resistors. Well, actually, that's not what I want, because that would just be equivalent. That's not different. Okay, so what I'm going to do is I'm going to stick 2 resistors in series here. So you would do these first. So let's let's call those, what do we call them? 2, 3, 4, 5. So we would find an equivalent resistance. We might call it equivalent resistance A, which is just the sum of those two resistances. Okay. So then the circuit would become something like this. You'd still have the first resistor. You'd have these two resistors which are in parallel. And then you would replace these two that are in series with just a single equivalent resistance like this. So this would be equivalent resistance A. This would be equivalent. This would be resistance 6, resistance 7, R2, and R3. So what we've done is replaced 4 and 5 with equivalent resistance A. Then here, because these are in parallel, you'd say, let's say call that equivalent resistance B is 1 over resistance 2 plus 1 over resistance 3. So you'd add those two together and take the reciprocal, and that would give you the equivalent resistance of that one. And then here you would have, say, equivalent resistance C, but the formula would be 1 over equivalent resistance C is 1 over equivalent resistance A plus 1 over R6 plus 1 over R7. So that would give you the equivalent resistance for that part. And then you could make it into this circuit. So this would be R1, this would be R equivalent resistance B, this would be R equivalent resistance C. So these two become that, these three become that. And then you could find equivalent resistance D, and that's going to just be R1 plus R equivalent resistance B plus R equivalent resistance C. And then you just, except there's no 1 over, because these are just, so the equivalent resistance D, which we're going to replace all of those three with, is just add those together, because these are now in series. And then once you have the equivalent resistance D, you could find the current through the circuit, because I let it fall out, but you have some voltage here, which I don't know what I called it. I didn't call it anything, so let's say it's voltage. So once I've simplified all those resistors down to one resistance, here's the voltage, then the current is just equal to the voltage, the applied voltage, divided by the final equivalent resistance. So that's how you can find the current through the single equivalent resistance. Now to go back a couple of steps, you'd have to you'd have to say that you'd have to go back in this. The voltage across here is the total voltage applied, and then you could figure out the voltage across each one of these by taking the current, which we know goes through all of them, this current that I would calculate previously, go all these three resistors, calculate the voltage across those, and then I take those voltages and I go one more step back. I'm not asking you to do that, but you will have to reduce a group of resistors down to a single equivalent resistance. Okay, so that was that. We already talked about RC circuits in the previous test, so we don't need to do that in this test. That's pretty much it for chapter 18. So what did I say it was? It's basically doing this stuff. Equivalent resistors. Oh, Kirchhoff's law, which we didn't. I'm surprised. Where is that? Must be somewhere in chapter 18. Yeah, okay. So 18 does Kirchhoff's laws, and that is going to be a separate problem, so you don't have to worry about that on the test that you need these notes for. Okay, so the next thing is chapter 19 stuff, which is magnetic fields. And these problems are pretty easy. So you've got three basic scenarios. You've got ones that involve forces, and the force, this is a force on a moving charge. And the force is equal to the charge of the moving charge times the velocity of the moving charge times the strength of the magnetic field that it's moving in. And then you also have this other term, which is if the angle between the magnetic field and the velocity of the charge is not perpendicular to each other, but we're not going to worry about that. So, you know, there could be a problem where I give you the charge, the velocity, and the magnetic field. Now, one thing that you do need to look at is the right-hand rule, and I'm just going to worry about this for the first two cases, the force on a moving charge. So you probably need to read that. But basically, you take your finger, I'm going to tell you what it is, and you can look it up and make sure you understand it. You take your fingers, and so I'm going to write this down. Fingers in direction of the velocity. Then you curl fingers in the direction of the magnetic field. So if they're like this, that's in, and if it's like this, it's out. So if it's into the screen or the paper, then you curl, you have X's, and if it's coming out, you have dots. And then your thumb is the direction of F, and these are all for positive charge. Opposite for negative charge. Okay, so that's the rule. Now, if you're doing a moving charge, you put your fingers in the direction of charge. If you're doing a force on a wire, then you're doing direction of the current. Okay, so that's first. Force on a moving charge, here's the right-hand rule. The next one is force on a wire. So you've got a current moving through the wire, and the force is equal to the current times the strength of the magnetic field times the length of the wire. I'm going to let you write these down, so that's why you got to listen to me talking. If you just write these down without listening to me, you're not going to know what you're doing. So Q is the charge in coulombs, V is the velocity in meters per second, B is the magnetic field strength in terms of Tesla. Over here, force is in newtons, current is in amps, B is magnetic field strength in Tesla, L is the length of the wire. Okay, make sure you can use this same rule down here. But in this case, fingers in the direction of the current. And then the final one is torque on a loop. And the torque is equal to the current times the magnetic field strength times the area. So that's the current in amps. That's the magnetic field strength. And in Tesla, this is the area of the loop. So if it's a circular loop, pi r squared. If it's a square loop, this tied the dimensions of the two sides. If it's a rectangle, the same thing. So going back to all the way back to this problem where I gave you the resistivity, the length, and the radius of the wire, I could follow on from this question. After you've calculated the current, then you could use that current in the last two equations I just gave you, plus any information about, if it was a wire, and I'd have to give you, say, the distance from the center of the wire to some point. That would be the one where you'd use if I wanted to, if I just wanted to figure out what the force on the wire was. So you'd be able to get the current from all this information, and then once you had the current, you could use that to either calculate the force from this equation, or if it was a loop, then you can calculate the torque on the loop. Now, there's one thing I missed here, and that's N, and this is the number of loops or turns. So the more turns you have, for each turn you get an additional amount of torque. So I could use those previous equations to calculate the current. If I gave you the magnetic field, the area here would be related to the number of loops, because the length, and this is the length of the total amount of wire, is going to be equal to in this case, not the area, but the circumference, or the perimeter, I guess would be the right word. That way you could so whatever shape loop, you take the circumference of the loop times the number of loops, and that would give you L. So if I gave you the length of the wire, you could figure out the number of loops by the dimensions of the thing too. So you can use this equation to kind of relate the amount of wire to the number of loops. So think about that. So those are the three equations relating force to magnetic field strength and charge and velocity. The charge and velocity come out through the current, basically, on this case. And then you have the next three equations, which are the calculating the magnetic field. So this is the magnetic, here we were given the magnetic field, here we're calculating the magnetic field. So we have around a wire, and you can determine that using two ways. You can use Ampere's law, or you can use this other one, this Biot-Savart law. So those are the ways you get it. Anyway, the result is the magnetic field strength at any radius. So here you have a wire, and then there are these magnetic field lines that are going around, and so these are, and they go a certain direction depending upon the direction of the current. So these are the magnetic field lines. This is the actual wire, and so if you want to find the magnetic field at a certain radius distance from the wire, it's just equal to mu0, which I'll give you on the test, times the current divided by 2 pi times the radius. So again, I could just give you the current flowing through the wire. You're given this. I give you the radius. You plug it in. You get the answer, and the answer's in Tesla. The second one is the magnetic field inside a loop or coil. And this is derived again through Ampere's law, or I think you probably could do it using this other method that we talked about, but it's easier to use Ampere's law, which I'll just state in a second. We don't have to use it, but just for review. So here it's just B is equal to mu 0 times I over 2R. So the pi things falls out, and what you have is you have a coil of wire, and here's the center of the wire, and it's, the current comes in, and there's like a little break here, so that you have to have two wires here. So the current comes in, goes around the loop, comes out this direction. So it goes in here, comes out there, and right in the center. So the distance from there to there is R, capital R. And what's happening is all these magnetic fields due to the wire, so due to this phenomenon, all add together to give you the total magnetic field strength in the middle. And if we have n loops, then we have n times the magnetic field for a single loop. For multiple loops is the magnetic field for a single loop times the number of loops, just adds on to each other. So mu 0 is given, I is the current, n is the number of loops, r is the radius of the loop. And this has to be right at the center of the loop. And then the final one is these solenoids. And a solenoid is kind of like this, but it's got a length to it. So it's a coil of wires, you have some kind of length. Let's call that L. And then there are n loops. So however many this thing is wrapped. And you can calculate the number of loops per length. So say it's 2,000 loops over 0.1 meters. You're going to get so many loops per length. And the magnetic field inside this solenoid is constant, and it's equal to the magnetic field strength is equal to mu 0 times I times small n. And if you look back at these previous examples, we've got the number of loops divided by the length of the dimension. So it's loops per some kind of dimension. In this case, it's L is the dimension. Here, R is the dimension, but it is still loops per meter or something like that. And so N has loops per meter. It has the same unit, so everything's going to work out okay. So you can see that the more loops you have per length, you're going to get a higher magnetic field, higher the current. So again, if I give you a problem like this, you just have to plug it into the equation, and that's easy. So you just got to recognize what they are and make sure you're very explicit about what the units are, and if there's anything in millimeters, change it to meters. If centimeters, change it to meters. Okay, so I've looked at the test, and I think I've pretty much covered everything that we need to discuss. So the only other two items that we've already discussed before, was the RC circuits, which we covered in the last test, and Kirchhoff's law, which we're going to handle in a separate problem. So that's it. Should be pretty straightforward.